Welcome to a lesson with Dr. Powell. Let's look at another example of partial fraction decomposition. This time, let's look at a fraction where the base is a quadratic raised to a power. Instead of a linear term like x minus 1 raised to a power cubed like we had last time, we have quadratic. We're going to kind of do the same thing though, but we're going to look at expansions in terms of powers of x squared plus 1. And ultimately, we're going to assume that what we have in the numerator, even if it's smaller like this, we're just going to assume that it has a power less than the denominator down here, and that its expansion is going to be as follows. It's going to have something with x squared plus 1 to the first plus something times x squared plus 1 to the 0, which is just 1. Okay. So now notice we're only going to the first power here, and that's because this is a 2. We're just going up to there. Now, how does this really work or make sense? Part of that is because what do the coefficients look like? So like with a base 10 expansion, the coefficients are always less than 10. In this case, it's not less than, it's degree less than whatever this is. This is degree 2. So we want something that has degree less than 2, so we'll take degree 1. Something like ax plus b. And then over here, something like cx plus d has degree less than what we're taking powers of. So these are like the coefficients there. Now, if you work this out, notice if you multiply this out, you're going to get an x cubed out, which makes sense because we want degree less than this. And if you multiply this out, you have an x to the fourth. So this works perfectly fine. This is the general form, assuming that this guy will have a smaller degree than the denominator. Okay, so somehow we can rewrite this fraction as follows. First, the numerator, 1, can be rewritten like this. And then the denominator can be rewritten with an x squared plus 1. Now, these guys cancel. Let's see, x, right? These guys cancel, right? Oh, this is squared. Squared, right. Okay, good. So all over an x squared plus 1 quantity squared. Okay, got to remember that. So 1 over x squared plus 1 quantity squared. So we're dividing everything by x squared plus 1 quantity squared. And then here, this cancels with one of those powers, but you still have a fraction. That was important. All right, and then you have that. So this still simplifies, but it doesn't look as nice as maybe it did in the linear case, but it's still workable. Okay, so this is how it decomposes, this is the general form. So we take powers, so this is raised to a power, so we take powers up to that power starting at 1, and then the form of the top is always just 1 degree less than whatever we have going on here. Okay, so great. So this is kind of what we're looking at. This part is going to be equal to that, and we got to find out what these A's and B's, this A, B, C, and D are. So let's work through that one. Okay, so we have 1 over x squared plus 1 quantity squared, and that's equal to, let's see, what did we have? Something like x plus b over x squared plus 1 first, plus it was a c. You just need to use anything that generically describes a linear term, something with degree 1, cx plus d all over x squared plus 1 quantity squared. Okay, so let's take a look at that and see what we can do. How do we find this A, this B, C, and D? We basically follow the same idea. We can plug in different things to make this work. Okay, and to make this work. Now, if we want, here's another procedure that we can use. So last time we used just plugging in different things to get stuff, and that works just fine. There's another way we can do this. We could multiply both sides by x squared plus 1 quantity squared. Can you see what that would do? This part right here would turn into 1 if we multiplied it by x squared plus 1 quantity squared. Here, the square and the 1 would reduce to just multiplying by x squared plus 1. And over here, you'd get full cancellation. So this is an alternative method, which sometimes can be actually quite useful. Then you can multiply this out, FOIL it out. So we get ax cubed. And then we have, looks like, plus bx squared plus ax and plus b plus cx plus d. And this is equal to 1. All right, something to keep in mind is this is an equality of functions, which is also an equality of polynomials. Now, if two polynomials are equal, that means their coefficients are equal. One is a polynomial because it's 1 times x to the 0. So notice that the x cubed coefficient over here is a 0. That means that x cubed is equal to 0x cubed, which means that guess what a is? A is 0. Okay, what about bx squared? That's the x squared part over here. And that's equal to 0x squared over here, which means that b must be 0 as well, which actually means that this guy is completely gone, 0. Okay, now over here, let's take a look at what we might be able to do. We have, let's see, so a is 0, b is 0, and we have 6 plus d. We know d must, let's see, okay, we know d must be 1 because that's now the constant term. So d is equal to 1, and c, which is the x part, must be 0. Well, this actually tells us something right here. We attempted to use partial fraction decomposition to help us out, and really, maybe our choice of integration wasn't, our fraction wasn't the best fraction for this particular this particular type of procedure. Why? Well, the numerator didn't really have a nice simplification into this type of form anyway that we were after. So it just was what it was. So we really didn't get anything additional here. Now, keep in mind, this would still have been required a little bit work to actually integrate. So we have this, and we're kind of back to the wire. Actually, on this one, it might even be useful to attempt something like a trigonometric substitution or something like that, because you notice you have an x squared plus 1. That might actually come in useful and handy instead of using partial fraction decomposition. But at least we tried, and along the way we saw kind of the procedure that we had for x minus 1 cubed, but we saw how it can work even for for powers of something else like x squared plus 1. And we also saw another technique that we can use, equality of polynomials, equating coefficients. So we have one polynomial on this side, one polynomial on this side. Their coefficients are the same because they are, as functions, the same function. Their coefficients must be the same if they're the same polynomial. So using that idea, we actually could quickly deduce that, yes, we really didn't gain anything in this particular decomposition. Thanks for watching.